I constantly hear physicists claim that there is something wrong with our understanding of the universe. It's an argument they frequently use to justify new experiments, a better detector, a new telescope, a bigger collider. At the same time, they'll also tell you that try as they might, they can't find any evidence that disagrees with their best existing theories. You've seen the headlines. Einstein was right again. Yet another anomaly gone. So what's going on? Do we have evidence of new physics or not? That's what we'll talk about today. In a recent article in the CERN Courier, Assistant Professor Carrie DiPatrilio argued for a larger particle collider. She wrote that we know the Standard Model is not the complete picture of the universe. Experimental observations and theoretical concerns strongly suggest the existence of new particles at the multi-TeV scale. TeV stands for tera-electron volt and is a measure of energy. The multi-TeV scale is what the new collider would test. There are no observations or concerns that suggest anything at the TeV scale. Another example, in a recent press release, Jim Fast from Jefferson Lab was quoted with the statement, "We know there are some things wrong with the Standard Model." He said this to explain why we need a new experiment to measure the weak charge of the electron. Makes you wonder how he knows that. Is it those observations or concerns that don't exist? It's been going on like this for a long time. Already in 2018, the then director of Fermilab, Nigel Lockyer, told the BBC that we need a bigger collider because everybody believes there's something there. From a simple calculation of the Higgs mass, there has to be new science. That is, of course, also wrong. For starters, no one can calculate the Higgs mass. It's a free parameter. It's determined by measurement. What DiPatrillo, Fast and Lockyer have in common is that they are all experimental particle physicists. Experimentalists in this field, for the most part, just repeat theoretical arguments. If you push them, they'll admit that they don't really believe what the theorists say, but if it brings them money, it seems they're willing to put their disbelief aside. So let's look at the most commonly used arguments according to which there has to be new physics that supposedly justifies all this investment. It's a really long list, and the heat death of the universe is only 10 to the 100 billion years away. So for today, I've just picked the most common claims. That's the mass of the Higgs boson, quantum gravity, dark matter and dark energy, neutrino masses, and the lack of antimatter in the universe. We'll look at those one by one, starting with the mass of the Higgs boson. In the foundations of physics, we currently use two different theories. One is Einstein's general relativity. Yes, that guy again. Einstein taught us that the effect we call gravity is really due to the curvature of space-time. The other theory we use in the foundations is a quantum field theory, imaginatively named the Standard Model of particle physics. It collects the known elementary particles and the three forces that hold them together, the electromagnetic force and the strong and weak nuclear force. The Higgs boson is one of those particles in the Standard Model, and its mass is a free parameter. This means you measure it, and then you use it for further predictions. There's nothing wrong with it. So why do particle physicists keep going on about it? I believe it's a mistake similar to the mistake that once made physicists think that black holes don't exist. They're confusing mathematics with physics. The first description for black holes came from Karl Schwarzschild. In his equations, there's a singularity at the horizon of a black hole. That there's a singularity doesn't mean the maths is singularly incomprehensible, though there's that. It means that some maths thing returns the value infinity. This seemed to suggest that black holes are unphysical, a mathematical possibility that doesn't exist in reality. It turned out, however, that the singularity at the horizon is an artifact of the particular mathematical description that Schwarzschild used, and that it has no physical counterpart. So there's nothing physically wrong at the black hole horizon. This becomes apparent if you calculate what you can actually measure. For example, what you'd experience if you crossed a black hole horizon. The answer is nothing. The horizon isn't a physical thing. Only problem with it is that you can only cross it one way. What happens in Schwarzschild's equations is that some mathematical quantities look weird, but once you ask what you can measure, everything is normal. That's why we no longer think there's something weird going on at the black hole horizon. There's a singularity in the middle of a black hole, but that's a different story. I'll get to that in a minute if you let me, but first let me wrap up the thing with the Higgs mass. The mathematics of the Standard Model says that quantum fluctuations make a large contribution to the mass of the Higgs boson. Physicists worry about that, like they worried about the singularity in Schwarzschild's equations. But like Schwarzschild's equations, the quantity they worry about can't be measured. Only thing you can measure is the mass of the Higgs boson itself. They're arguing about something that doesn't exist. It's like complaining that Harry Potter's magic spells violate energy conservation. Maybe they do, but so what? They're not real. Another argument they sometimes make is that the Higgs boson is different from the other particles in the Standard Model. And that's correct, but just because it's different doesn't mean there's something wrong with it. And in any case, the argument that there's supposedly something wrong with the mass of the Higgs boson was what led to all those wrong predictions for new particles at the LHC, like supersymmetric particles and additional dimensions and gravitons and whatnot. So whenever a particle physicist tried to tell you there's something supposedly weird about the Higgs boson, keep in mind they already fooled us once. Let's then talk about something more interesting. As I said, we currently use two different theories in the foundations of physics, general relativity and the Standard Model. Unfortunately, these two theories don't cooperate. It's because the particles in the Standard Model have quantum properties. For example, they can be in two places at once. But general relativity is not a quantum theory, so the gravitational field of those particles can't be in two places at once. This makes no sense. It's just mathematical rubbish. What we need to solve this problem is a theory that gives quantum properties to gravity, or, since Einstein said that gravity is really an effect of space-time curvature, a theory that gives quantum properties to space and time itself. It's usually called quantum gravity. The theory of quantum gravity is also believed to resolve the singularities that we have in general relativity at the Big Bang and inside black holes. It's because in these cases space-time curvature is extremely large, and the quantum fluctuation of the geometry should become important then. And this is something we know is wrong with our current theories. We're missing a theory of quantum gravity. But particle physicists usually don't talk about this. It's for a simple reason. Gravity is an extremely weak force compared to the other forces, electromagnetic and the two nuclear forces. You can't measure gravity if you look at single particles like those in the Standard Model. Their gravitational pull is just too tiny. We can only measure gravity for large objects because it's different from the other forces in the Standard Model. It can't be neutralized, so it adds up. If you form large chunks of matter, the nuclear forces become unnoticeable and the electromagnetic force usually becomes fairly weak, unless possibly you're lying in an MRI machine, which is why you really shouldn't take guns anywhere near those things. That's why testing quantum effects of gravity isn't something you can do with single particles. You take something bigger. I talked about possible experiments for quantum gravity in a previous video. For today, I just want to say, yes, quantum gravity is an issue we need to resolve, but particle physics won't help you with it. Next point, dark matter. If we take Einstein's general relativity and all the particles of the Standard Model, we run into a problem. It's that these two together just don't correctly describe many observations in astrophysics. There are two ways that physicists are trying to resolve the problem. One is to add new particles. That's the idea of dark matter. The problem with dark matter is that the hypothesis is so flexible it can be adapted to everything. Whenever an observation doesn't fit a prediction, astrophysicists change the dark matter model. One of the least understood problems in the universe is Elon Musk, but I wouldn't be surprised if dark matter would soon be used to explain that too. The other way to explain the mismatch between prediction and observation is to change general relativity. This is known as modified gravity. But modified gravity can't be tested with particle colliders or particle detectors. Indeed, it generally can't be tested in the solar system, because the modifications only become noticeable far away from big, massive things like our Sun. That's why particle physicists don't like modified gravity. They can't get any money out of it. They prefer the idea that the observations are explained by dark matter particles, because looking for particles is what they do. But not any particles, no. Specifically such particles that can be either produced in the next particle collider or at least measured in one of their detectors. The problem is that even if dark matter is made of particles, which it may not, there's no reason why it should be a type of particle that can be produced at the next bigger particle collider or be measured with the next bigger experiment. If you point that out, they'll tell you that, well, at least you can rule out some ideas. Sure, but that's like saying, I don't know where your car keys are, but if you give me $10 billion, I'll check if they're in my fridge. At least that way we can rule out some ideas. Deal? So the observations usually attributed to dark matter are a real problem that requires solution somehow, but that solution doesn't necessarily require changing the standard model, certainly not at the energies that a next bigger collider could test. What's with dark energy? The observations attributed to dark energy are well explained by a cosmological constant. That's just a constant of nature, end of story. In terms of an explanation, a constant of nature is as good as it gets. Some theorists try to argue that the constant is not constant, but really a quantum field that's made of particles which you can then look for with a particle collider. But that's an unnecessarily contrived hypothesis, of which, again, there are infinitely many, so testing them is an unpromising strategy. Let's then talk about neutrinos, which are probably the new physics argument that causes the biggest confusion. Neutrinos are one of the particles in the Standard Model. There's 3 of them. Neutrinos are, as the name suggests, electrically neutral. Because they have no electric charge, they interact very rarely and are hard to measure. We have known for about 20 years that neutrinos have masses, and there's been a Nobel Prize for that. Consequently, if you look up the Standard Model on Wikipedia, it'll tell you that, of course, neutrinos have masses. But a lot of theoretical physicists would tell you that neutrino masses are physics beyond the Standard Model. I think that's bad terminology. But here's the rationale. We know that neutrinos have masses, but we're not sure how they get them. The issue is that other particles, like the electron, come in 2 versions. We call them left-handed and right-handed. And the mass of the electron comes about by an interaction between its left-handed and right-handed version and the Higgs boson. But for neutrinos, we've only ever observed the left-handed version, so we can't do that. There are 3 different options to give masses to neutrinos. The first option is to just postulate that right-handed neutrinos exist, we just haven't yet observed them because they're too heavy. The second option is that neutrinos are different from electrons in that their right-handed version is the same as the left-handed one. This is called a Majorana particle. You can then take just 2 of the neutrinos we already know exist and couple them to the Higgs, and they get masses. If neutrinos were Majorana particles, that would allow for a particular type of radioactive decay of neutrons, known as the neutrinoless double beta decay. There's an experiment called CATRIN looking for this. So far it hasn't seen anything, but it's only just begun collecting data. The maybe most popular option is a combination of the previous 2, in which case the right-handed neutrinos are too heavy to be produced at the next bigger particle collider. The third option is that you create a mass from the left-handed neutrinos and the Higgs without making them Majorana by coupling it to a pair of Higgses. For this, you don't need any new type of physics, but if you do this, it creates a mathematical problem in the Standard Model. It would then break down at high energies. This could mean that at those high energies there'd be new particles popping up, but the energies for this are again well out of reach of the next bigger collider. This means the issue with the neutrino masses is similar to that of quantum gravity. We know that there has to be some solution, some new physics, but the solution becomes necessary at energies so high, they're orders of magnitude away from even the next bigger collider. Though in both cases there are other experiments that could shed light on the situation. Another reason that I often see particle physicists name to argue there's new physics is the alleged puzzle that there's more matter in the universe than antimatter. They believe that the universe should have been created with equal amounts of both, so that they completely annihilated, leaving behind nothing but radiation, which is clearly not what we see, unless you are radiation, in which case, thanks for watching, don't forget to subscribe. The supposed problem is quickly solved. There's no reason why the universe should have started out with equal amounts of matter and antimatter. I think this argument sounds plausible to non-experts because they've heard that we know from Dirac something about the symmetry between matter and antimatter. And that's right, but all that Dirac taught us is that antiparticles exist. His revelation says nothing about how many of those particles there are in the universe. I explained this in more detail in an earlier video. So when it comes to the matter-antimatter asymmetry, there's nothing in need of explaining in the first place. Particle physicists also sometimes claim that observing violations of certain types of symmetry, known as CP symmetry, will help us explain this. It won't. No matter what they measure about CP symmetry, we'll still need initial values for the amounts of different types of matter in the early universe, because it's how our current theories work. In summary, the mass of the Higgs boson, dark energy, and the matter-antimatter asymmetry require no further explanation and certainly no new physics. But it's correct that we know that new physics must exist. Two good theoretical arguments are that we are missing a theory of quantum gravity and that we don't know the origin of neutrino masses. We also have a good experimental reason to believe in new physics. That's the observations which are usually attributed to dark matter. Even if dark matter isn't the correct explanation, we still need some explanation. However, for none of this new physics do we have any reason to think it'll show up in any of the detectors that are currently under construction or at the next larger collider. If you hear a physicist say otherwise, they're making things up and think you don't know any better. But luckily, you're watching Sabina's channel, so you're not easily fooled. New physics is cool, no doubt, but as they say, you have to learn the rules before you can break them. If you want to get up to speed on the rules of physics, a great place to start is Brilliant, who have been sponsoring this video. Brilliant offers courses on a large variety of topics in science and mathematics. It's a fresh and new approach to learning with interactive visualizations and follow-up questions. Some of their courses even come with demonstration videos for experiments and executable Python scripts. They have a lot of content on physics, from classical mechanics to astrophysics, gravitational physics, and quantum mechanics. I like to learn new things on Brilliant, and I even have my own course there. It's an introduction to quantum mechanics and starts from the very basics. My course will introduce you to the concepts of interference, superpositions and entanglement, the uncertainty principle, and Buzz theorem. And afterwards, maybe you want to continue learning more about quantum objects or special relativity. If you're interested in trying Brilliant out, use our link brilliant.org/Sabine and sign up for free. You'll get to try out everything Brilliant has to offer for 30 days, and the first 200 subscribers using this link get 20% off the annual premium subscription. Thanks for watching. See you next week.